Hello, my structural analysis friends. In the world of structural engineering, there are a lot of terms thrown around related to structural components and connections, and a lot of principles of framing that are often just assumed by the experienced engineer. In this video, we're going to look at some of these different concepts and try to give you just kind of a little bit of insight into the thought process of how a building is framed or connected, or one member is joined to another. So without further ado, let's get started. There are a lot of structural elements that are needed in order to put a building together, and a structural engineer must be able to take advantage of all of these. As a young engineer, when I first came out of undergraduate, I knew what a lot of these items were, but there were still some that I wasn't very familiar with. And so as I was thinking of putting this lesson together, I started to try to think of, well, what were some of the terms that would have been helpful to know a little bit more about. And so that's kind of the focus of this particular lesson. Okay, structural elements, basically they divide up into three different basic categories. As a structural engineer, we're worried about all of them, but more often than not, we focus on two. Okay, they are the primary members and the secondary members, and then this last category for these first two would be more like, connection details for foundations. Basically, how is your building being attached to the ground? Okay, and that's usually accomplished through anchor bolts and bearing plates. All of these get designed in, say a steel class or a concrete class. Bearing plates are typically a steel plate or some sort of mechanism for spreading load out. Not real common in concrete. Anchor bolts are basically the bolts that are embedded or attached to the foundation that help hold the bearing plate, which is attached to the column, to the building. And so we can kind of work our way through that. Okay, the columns and girders then fall into a category that we call as primary members. Okay, basically what a primary member is a member that if something happened to one of these guys in a structural frame, a big portion, if not all of the building, would be compromised. Okay, you lose big areas of these buildings. It's often why you'll see different safety factors applied to these kind of members. You'll see different multipliers in the case of like live load reduction applied to these type of members. It's a very they're critical, basically. Okay, and so those are your primary members. Whereas the secondary members generally connect between primary members, okay, or supported by them. Like a beam is sitting on a girder, and a girder is tied to a column. That if I lost the girder, then anything that's sitting on top of it would come down. Okay, assuming gravity, of course. Okay, but there are some different types of secondary members and some different examples of how they're framed and how they're kind of put together. And the purpose of this video is then to try to kind of explain some of the assumptions that a structural engineer uses in terms of a structural layout. Now, depending on your analysis and your design, the sizes and shapes and arrangements of these can be varied. So that's kind of what we're looking at. But with some rules of thumb in our pocket, so to say, with the use of some rules of thumb, we can get kind of a sense of typical ranges of sizes, for say a beam, or for trusses or bar joists, open web steel joists kind of things, purlins, girts, and then of course any sort of bracing. All kind of those sizes kind of get dictated by the arrangement of the primary members. If the girders are really close together, my beams are very short. But if they're really, really long, like I need open area over an auditorium or a big convention center, then maybe I need a truss that's hundreds of feet long. And so those designs are all dictated by the geometry and the layout. Now, the way that this typically works is that a structural engineer either generates the framing plan or is given a framing plan by an architect, who has gone through the effort of arranging the room for its utilization. What's an office, what's a meeting room, what's the cafeteria, and those kind of things. So once you receive that, then the part of the puzzle for a structural engineer is figuring out where can I put pieces to hide them in order to maximize the use of the room. I mean, nobody wants a column in the middle of your living room if you can avoid it, because it's obstructed view seating. So those kind of issues are part of the game that we play, and so we're going to focus on some rules of thumb to help us to try to avoid those scenarios or minimize them. Sometimes you can't avoid them. Sometimes I have to have a column somewhere that I don't want it, but you don't have a whole lot of choice. Okay, so what I've done is I've kind of gone through and I've pulled from some outside resources some diagrams of some different parts, and we'll kind of work our way through this. And for those of you in the class, you'll have access to these paper notes, and you can kind of read the text on your own. But I'll kind of point out some highlights of some of the different items that are showing up on this list. Okay. All right, so we're going to start off with kind of some typical structural dimensions that we're dealing with here. Okay, so the first thing that we have, oops, get this turned the other way. There we go. Okay, is that typically in a normal framed building, now definition of what is normal, okay, it's we're not looking for extremely tall structures with extremely large open areas, just a typical framing arrangement. These rules of thumb have served me very well over the years. Okay, typically to come up with an economical shape of, beams and girders, my column spacing is dictated to usually end up being somewhere between 25 and 40 feet. 40 feet starting to get a little bit long, 25 starting to get a little bit short for usable space. But that's the arrangement. So if I can get a column spacing somewhere in there, then I would classify this as a normally framed building, and there's, I will reduce my chance of having potentially, oversized beams or oversized girders or some sort of, structural imbalance kind of situation. Okay. The other rule of thumb that I use is that between floors, which is what we call the story height, okay, typically that's somewhere between 12 and 15 feet. Now, I define story height as the top of floor above to top of floor below being that distance. So in that space, you have, say the thickness of the beam, I have the clear height, and so if you have anything like a drop ceiling or anything that brings that roof line artificially down, the ceiling line, I guess, on that, then you can quickly eat up into this. So I tend to prefer to push more towards 15 feet. For a non-flush framing situation, which we talked about in the last video, normally that steel framing can account for as much as 2 feet of depth that you lose, which is good if you're trying to run plumbing lines or air conditioner, HVAC, tunnels or conduits or those kind of things, because you've got space to run those and you can conceal them. But, if this ceiling height is 12 feet and then I lose 2 feet, that's 10 feet of height. And you start kind of getting into this kind of low ceiling structure. Now, think about this in terms of a tall building, right? The bigger I make this number, the more floors I add, the taller my building gets. So there's a balance on this that, if I'm doing a multi-story high-rise type building, then maybe I'm pushing more towards 12 feet with flush framing in order to keep the height of the building down, so that I'm not paying for all that extra steel in the height of the columns or whatnot. And so that's where there's kind of this game, and it kind of depends on your situation that you're looking at. Okay, now one thing to point out is that I've kind of highlighted this and says that that this assumes normal loads. Okay, and normal framing, nothing unusual, but there are always exceptions. Even the normal stuff has exceptions to it. So as a structural engineer, you have to be prepared to be able to handle those. But through my experience, these dimensions have always served me well as kind of a starting point for the framing process. Okay, all right. So the first piece of the packet, the way this packet is set up, is it starts at the foundation and then it works its way up and talks about a lot of different pieces of what structural engineers use to make these connections. And so the first thing they start with connections to the foundation by means of an anchor bolt. Okay, so I've got give you kind of a sense of some of the size of an equivalent cube of concrete versus steel. Concrete weighs about 150 pounds, but steel has a density of about 490, and so this gives you kind of a sense of what a 1 by 1 foot plate of these thicknesses will give. So a 2-inch thick plate weighs about 80 pounds, an inch and a half weighs about 60 pounds, and so forth. So this just gives you kind of a sense of the weights that we're talking about on these. Getting into a 2-inch, 1.5, or 1 is not uncommon for a base plate on a steel column. All right. Now, to make those connections, I'll point you down to this picture, okay? And this is kind of how an anchor bolt works, all right? So imagine this frustrum here is the top of the foundation. It could be rectangular, it could be any shape. That it's the column footing. Then there are anchor bolts that are typically they're cast in at the time the concrete footing is placed, and then they have some sort of nut and a bolt on it that goes through holes in those base plates to make the connections. Now, they can be done after the fact as well, like if something is misaligned or if you forget to put one or decide to add something later, you can use some sort of quick insert kind of epoxy grouted drilled type of anchor bolt as well, but typically these are what are preferred. It does require you to be careful during the fabrication. It does have some issues with getting these things located properly, at the time of setup, but then again, that's always a challenge. So this is one of the reasons that a lot of times we will slot a hole in a bearing plate or oversize it a little bit more, just to give you a little bit of room in case that anchor bolt kind of leans over as it's being connected. All right, let's see. Moving on to the next page. So once you have the anchor bolts in, then we get into, this is kind of how the base plates are connected. Okay, a lot of times there are some sort of shim or some sort of leveling nut to be able to kind of get that base plate level, because when you put these plates on, sometimes especially if they're pre-mounted to the bottom of the column, and I'll show you some of those in a second. It's possible that they're out of plumb or slightly out of alignment. This gives you a little bit of room to be able to. My focus just went out of focus. There we go. Okay. It'll give you some sort of way to recorrect that, because at the end of the day, I don't care how level the base plate is. It's the verticality of the column that's connected to it that I'm worried about. So as long as it's not too far out of line, then we're okay with the plate being a little bit. But that's what these shim packs or these double nut setups will start to do for us. But basically, that's how it happens, is these base plates get bolted down through. So here are the anchor bolts that were laid in place. Okay, so once you get the anchor bolt figured, or the base plate figured out that it's anchored down, now it's, well, how do you make the connections to the bottom of the column? Okay, and so one way is that you could do some sort of pre-drilled angle that picks up the flanges. So I'll point you down to these three types of arrangements. Okay, this is what we call a flange connection, a bolted flange connection. You can see there are two bolt holes that go into the flange of this structural I-beam column that's here. This is called a web connection, okay, in which the web is this piece of it. And so again, kind of the same idea, but now they're bolting those into the web of the beam. Okay, there are cases where they do both, or combine them, okay. The one I like to do is the welded base plate, partially because I can build this in the shop. I fabricate the column, put it in the fab shop, and then mount the base plates onto it, and then it's one piece that's already preset. And then if I use those shims or those leveling nuts, I can make sure the column remains vertical, and it's just a bunch of less extra pieces that have to be aligned. Every time you drill a hole, there's a chance that it doesn't match on the member that it's going into. It's just there's some potentials for issues with here. So my history has always been using welded base plates on those, but I'm not going to say that they're not useful with the other ones. These are just, to me, are the more common that I've seen. Okay, so that's what I kind of prefer on those. All right, so then we move into the columns themselves. Okay, and so we get some pictures that look something kind of like this. Okay, that we have a girder spanning across multiple. These would be pipe columns instead of I-beam columns, and so this girder runs across the top, and then they've made a connection of some plate and some sort of hole that's gotten drilled in to a plate on top of the column, and that's how they make this connection. This is a common style in residential construction, like in your basement. If you go down and look and you have a pipe column in your basement, generally it's holding up a steel beam that holds up then the wooden roof or wooden floor joists of your house. So that's a pretty common setup. So we can make columns a lot of ways. So you've seen the pipe column, you've seen the I-beam in the last page. You can also build them up, and this is a kind of an angle box column that basically there's an angle from here to here and another angle from here to here, and then they weld down the length of it here to build this kind of tube. They're also prefabricated tubes, but lots of different ways to accomplish this. You can also do another kind of build up in which I have a plate for a flange, a plate for a web, and then I use angles to make the connections of all of those on these as well. Okay, so you can get non-standard sizes, but generally it's more cost effective to pull a size that is a standard rather than to build up your own. But sometimes this is what you do, so that's another option for you. Once you have your columns, you notice the columns, depending on how tall your building is, they have kind of certain lengths, and if our story height is 12 to 15 feet, a column generally can ship in as lengths as much as 40 before it gets kind of too spindly. And so, about every 2.5 floors is about the maximum length you can go on a normal column. And so we have to start figuring out, well, how do I connect one column on the bottom to a column that continues up? All right, so this is what we call, it's kind of a flush column connection, in which the column above and the column below are basically the same size, that I can just run a plate along the outside and then bolt those in. A lot of times we'll weld it to one side and then bolt to the side in the field. Field bolting is a lot faster. So that's one way that they can do that. If you have a change in sizes in columns, now I've got a much wider column here, and then this little bitty guy here. Sometimes you have to put the shim plate in to kind of build it out so that this splice plate can go all the way through. So that's not uncommon either for drastic sizes in columns as you go up the building to be able to do that. It's not a big deal. There are, when you take a steel design class, we'll show you how to dimension these and how to come up with the thickness and how to figure out how many bolts that you need to be able to make these connections. But that's kind of the logistics. So when you hear of a non-flush column splice, that's what they're talking about. And that's the purpose of what this video is to kind of give you some terminology that you might not have heard before as you start to kind of work on those. Okay, all right. Okay, then we get into kind of, types of connections. So this is, similar to what we had. We have a girder coming into a column, and so this is a bolted connection. They really favor the bolted connections here. And I get that, because sometimes if you're not careful when you ship these, if you pre-weld something, these guys can get bent and misaligned, and that can cause a problem in the field as well. But generally, if you're careful about the way you pack these things, it's just a much faster install because these clips and stuff are already on. They don't get lost or misaligned or on a different truck coming out to the job site that you have to wait to be able to make all those part connections for. Okay, but these are all the different types of connections. Once you get past the columns, now we figure out, so this is a case where the girder runs over the top of a column. Okay, but you can also have a case where the girder comes into a column, into the side of it. And so then we come up with what we call a seated connection, and that's basically you put an angle here on the bottom, you put an angle up on the top. You can have web connections that go into the web of the beam and then bolt into the column. And again, a lot of times, on one end of a beam, we'll pre-weld these onto the beam so that you don't have all these loose parts, and then all I do is align the holes on the column, and then we can bolt it in the field. And that's one way. So this is kind of a seated connection, if you will. Sometimes you have the tops and the bottom, sometimes you don't, sometimes it's web only. All of these have different behaviors. This would probably model more as a fixed connection, whereas if I took the two on the top out and only had the one in the middle, this would be more like a pinned connection because now you've got a little bit of rotation. Okay, there's generally a little bit of a gap between the end of the beam and the column just to allow fitting and misalignment and those kind of things. Okay, all right. For beam-to-beam type of connections, we talked about flush and the kind of flush and non-flush framing. These are a couple of scenarios for the non-flush scenario. This is actually almost a semi-hybrid, because you notice that it's not flush with either the top or the bottom. Okay, so in our last video we talked about the semi-flush condition for this. This is a scenario where I have a big beam bolting or coming into the side of a girder and a smaller one coming in from the other side. Okay, and generally you want to be careful about this as well, because depending on the loads, this can actually cause a torsional effect into the girder. If you need a big beam, chances are you have big loads. Okay, whereas if you have a smaller beam over on this side, and if these are unbalanced, this girder kind of wants to turn, it kind of wants to, in this case, would probably want to end up rotating counterclockwise a little bit. Not all the way, but that would be a factor that you would have to look into in the design of your girder on those kind of things. This one's a pretty straightforward web connection, that it's a web connection into the beam, and then those will bolt, and typically they try to align the holes across the web so that they both sides can share. But that provides some challenges in construction as well, in that this beam, now I have to hold it in place while a crane comes up and picks up this one and holds it in place, and then we have to align both simultaneously and put a bolt through it. So this is a 4 or 5 man job to control this. 2 to control this with the crane and placement, 1 and 2 to control this one with plane and with crane and placement, and then 1 or 2 more guys trying to get this bolt lined up through all 3 holes. It's a challenge to build this, okay, but it's done. It's not a big deal. Okay, so lots of different ways to do this. If you need a flush connection on the top, a lot of times what they do is what they call a coped end, and you can see that the top surface of the beam is lining up with the top surface of the girder, and what they do is they basically notch out a little bit of the metal of the beam to make it so that you can raise it up. Otherwise, if you look up in this picture, see how the top of the beam, it would hit on the bottom side of the flange. You would never be able to get a flush connection without notching this thing out. And so this one, you can. Okay, and again, it can be bolted, it could be welded, or some combination of the two. But this is called a coped end. If this beam is the same size as the girder, then you can sometimes even cope both. Okay, but for most cases, it's generally a top cope on this one. Now, if you need a flush bottom for some reason, then you basically do the same thing. This is called a blocked end. Okay, and so it's almost like putting a cope on the bottom flange of this thing, and again, you get a flush surface on the bottom of this. Okay, All right. Okay. Other type of connectors that are pieces that you'll hear the term bar joist. That's called basically an open web steel joist. And that's these truss guides. If you walk into a Walmart or a Home Depot or something like that, then these are what we're talking about as far as open web steel joists or bar joists. And these are nice. They're very lightweight. They're prefabbed as a unit, and then you basically pick up the whole unit, and they're trusses. And you basically preset them. You know, you set your column in, you set your girder on it, and then these things just set directly on top. They're very lightweight. You know, 2 or 3 people can set them. They're prefab. They install very, very quickly. Okay, but they do have some considerations or some concerns for wind loads. Okay, winds on roofs, and these guys they don't play nicely together sometimes. So sometimes there's some extra things that you have to do, like ballast on a roof, or not as long a span for those for these trusses that are set up like this. But if you go in and look at like I say, next time you're in Walmart or Home Depot or Best Buy or any of the big box stores that you have, if you walk in there and look up, you'll see that they're very similar in length and similar in layout. So the thing that's nice about these is you can standardize them, and one shop you could produce 120 of the same piece that does the same job down the length of the building. Okay, and so it's a couple of little different ones at connections and locations, but the majority of these are mass produced. Okay, in the design, this was my first job out of undergraduate. I worked for a steel joist fabricator, and this is what we did. We tried to standardize these as much as we could so that the shop could set up and run as many of these things through the shop in tons per hour, dollars per hour. And so the more we got through the shop, the more money we made as a company. And so that was one of the challenges that we had, was to standardize this as much as possible. Okay. All right. Connections of bar joists, typically they sit on top of something. They can sit on top of other joists, or they can sit on top of I-beams. Typically there's some sort of what we call the shoe, okay, up here. And so for about 5 or 6 inches, and this guy sits on top of a beam, and then it's bolted or welded or something to the top of the beam. Okay. A lot of times, and you saw that in this last photo, if you notice, the bottom cord is this line right here. Okay, you'll notice that it stops short. It doesn't go all the way out to the girder. When it comes into a column, often they extend this. It's called a bottom cord extension, and then they have some sort of shelf angle or something, and that's welded to the column, and then this is welded to the shelf angle, and it basically gives you more of a stronger, not fixed connection, but a more rigid connection at the end places. Otherwise, if you didn't have this piece that's right here, this almost becomes like a pin and becomes more of a simply supported scenario. And so this guy will deflect a lot more, and you'll have some other issues that will arise. So those are all some things. But these are what we call bar joists or open web steel joists. They're basically trusses. Okay, and they come in all sizes. They can be very short, from 25 foot long, like maybe you see at Best Buy, to 40 feet, to even multi-span over football stadiums kind of thing, and they're 12 feet deep. There are lots of variety, and that's the advantage of these, is that you can prefab any roof profile that you want. These are parallel cord, but you could have scissor trusses, which are the case where they kind of look like that, which is often used in housing. You could have barrel, some sort of barrel truss, which gives you a rounded roof profile, which is often common over at auditoriums and those kind of things. They're very, very versatile, which is one of the reasons people like them. They're versatile, and they're easy to build, and they're easy to install. Okay, just you have to do some engineering design on the front end of it. Okay. So then we get into talking about purlins and girts and trusses. This is kind of the connection of, if you weren't doing a truss like the open web steel joist, you can build your own. And so you'll hear the term gusset plate tossed out, and that's what this piece is. Okay, and you can see that I have an angle that's come up. We've drilled a bunch of holes, and this plate bolts to those angles, and this member lines up with another set of holes on the same plate. And so there's some design that goes into work on these gusset plates as well. Let's see, what else we got? Purlins are basically, if you imagine that you have, some sort of beam system running between here, the purlins would be the guys that connect between those. Generally, they're not like the open web steel trusses. The trusses kind of act like a purlin, but these are on frames that are a lot closer together. Basically, they give you a surface for the roof decking to be able to connect to. And then girts are the same thing on the walls. I don't have a picture of that, for where the siding or the wall panel connects to the structural framing. Okay, and so they're they're very lightweight, generally channels or Z shapes, and they stand between roof trusses to provide a decking surface for those. Okay. As we talked about, you can do a lot with the different profiles, just by playing with the trusses is one of the reasons we like trusses. They're very easy to analyze, and they are very versatile in their arrangement. That I want a flat roof, I can put a box truss here. If I want a sloped roof, I put a triangular truss here, so forth and so on. And then you can kind of see some of the struts and the ties that are happening between the truss systems. So if these aren't too far apart, then a purlin would run from here to here, and then you have some sort of diagonal bracing, which helps kind of lock the whole thing together to keep one truss from moving relative to the other. So there is some lateral framing that we haven't talked about, and when we get to design classes, we'll do more with that. Okay, all right. And so that's the basic idea. And then how do you make the purlins connect? And then there's this is kind of an interesting detail that if you have a peaked roof and you lay a channel as a purlin on this side and lay a channel on the other side of the peak, well, now you've got this kind of strange empty cavity that has to happen, and so there has to be an insert piece or something that is used in order to make that connection come over the top of the ridge. And the ridge is the point that we're talking about here. It's the peak, if you will, as it runs down the length of the building. Okay, all right. There are eaves and soffits and those kind of things. These occur down at the ends. That's down here. So here's my truss again. And on your house, typically these are overhung from the outer wall, but the outer wall might be sitting about here, and then this is out, and that is a runner plate that runs from between the trusses or between the roof members, and then a soffit would be that undersurface down underneath. If it comes down and does something kind of like that. Here's my eave. So that's this piece, and then this is my soffit. It's SOFFIT. Okay. And so that's another term that you'll hear used a lot in structural engineering. Okay, now getting back to some wood construction. This was kind of a graphic that kind of shows, again, this is in your packet, you can kind of see some of the basic construction. Wood construction is a little bit more challenging in that we can't go very long distances without putting another wood member just because these are so lightweight. Normally these are 16 inches on center. But you can see that over openings, they'll put what we call a lintel or a header over the opening, and then this would be where a window goes, and then similarly over a door. I don't see a door on this particular wall, but kind of the sheeting and all of those. You can look at this picture, and we get what we call jack posts or king posts on either side of an opening, which kind of help to support the lintel and then to be able to carry the loads from the wall above. But you have to kind of build this box kind of set up around it. There's a kind of a floor plate. This doesn't show it real well, but if you look in between the verticals here, you'll see this little horizontal piece of wood that runs generally the length of the wall. This is called a sill plate. Okay, and then your floor beam is down here, and then there's another, a sill plate or a toe plate underneath that as well. But basically, you can prefab these walls and units, and then basically connect them all the way down through the beams they're sitting on into the structure that's holding up those beams. So all sorts of neat stuff. Here you can see that here's the eave again, and you can see that little horizontal surface underneath is kind of the soffit. Okay, and again, that's very common construction, at least here in the U.S., for doing stuff like that. All right, the last little bit that we want to talk about then has to do with kind of some secondary framing and some practical dimensions on here. So this kind of goes along with our idea that typically we put columns anywhere from 25 to 40 feet on center, and floor heights are 15 feet. Okay. A lot of times the secondary framing, such as beams and bar joists, they're typically placed at 4 foot on center. Okay. And there's a reason that we do this. Okay. There may be one oddball spacing at one end of a bay, but normally what they like to do is again, we're talking about repetition, is that we'll set, if this is my columns here, and then I have my girders going between the columns, then the first one goes 4 feet, and then the next one is 4 feet, 4 feet, 4 feet, 4 feet, and it just tallies up all the way over to here. And then when I get to the last one, if this bay, say, wasn't a multiple of 4, this guy gets an odd spacing, and that's fine. But what that does is it standardizes and most of the reason is that 4 foot is kind of what we call the magical 48 dimension. Okay, and there are a lot of things that come in 48s. Okay, the 4 foot dimension is important in construction for many different reasons. One reason is that metal decking for roofs comes in 4 foot, 8 foot, or 12 foot lengths. Okay, so what that allows you to do is if I run my decking, in this case left to right, and I start it here, At 4 feet, I end on this one. At 8 feet, I end on this one. At 12 feet, I end on this one. There's no extra cutting or trimming that needs to be done on the metal decking. Okay, you just basically take the sheet off, lay it on, and you have a surface at both ends, and then they come make their connections that way without having to do trimming. Now, again, because of the oddness in the dimensions, there will always be one end that has to be trimmed off. Because again, these sheets come in standard lengths, and you don't pre-order them to some odd length. They just come in big pallets of that size. So that's one reason is the decking. Okay, the plywood sheeting, which is your plywood, are come in usually 4x8 foot dimensions as single sheets, and then you can stagger them and attach them as well. Well, again, if you go back 4 foot on center, I can put one here, and then I could stagger the next one. It would span over 2, and then the next one I could span from here to here, so forth and so on. And that's the magic of the 48 dimension. Okay. The other thing that happens with these 4 foot dimensions is that if I put them on 4 foot dimensions, that my 2x4 wood framing, we said, normally occurs at 16 inches on center. And if you need a bigger stud size, maybe you go to a 2x6, generally that's at 24 on center. Well, both of these are multiples into that 48 number. 16 times 3 is the same as 24 times 2 is 48 inches. And so what happens is that if I have a stud that needs to come in here, then it lines up with my beam. My next one is directly underneath a beam, and my next one is directly underneath a beam. Everything lines up off of this magic 48. Okay, and so that's a very, very common dimension. Now, not always. Okay, get into steel construction, you can get away with some more regular shapes, but especially in wood construction and even in steel construction, I try to typically stick to this 4 foot dimension just because of that magic 48. But again, that's part of a constructability. It doesn't really affect your analysis from the load standpoint. I guess it reduces your loads on the members and lets you get smaller members as well, but that's an important dimension to remember, this 48-inch dimension, and why they do it. There's like I say, there's multiple reasons. So if you deviate from this, you got to have a good reason to do it. Otherwise, the guys in the field get a little upset with you. So anyway, that kind of sums us up for our basic structural framing and some basic tips and tricks and terms. We'll pick up with that next time. For those in my class, we're going to work on some framing exercises. Kind of trying to figure out, this is an architectural plan that came to you. How do we establish the framing on this? You can kind of see a grid. Each grid is 5 feet, and we'll work on this. Where do columns have to go, and then how do I start to lay this thing out? And that will be a class exercise that we'll do together to give you a sense. And then we'll ramp it up and get a little bit more challenging. We want to have a little bit of fun with it, right? So there's one with elevators and stairs, okay, and then there's an irregular shaped, and these are always fun to try to figure out. Where can I put columns? Where can't I put columns? And so forth and so on. So anyway, that's all we have to do. And then your homework, again, just so you have it, will be to do something. I'll give you an architectural plan that looks something like this, and you come up with one for that. Okay? All right. So anyway, that's what we have. So hope this has made sense to you. I hope it's given you a little bit of insight into some of the terminology that we've used and some more terminology that we will be using. As always, if you'll leave us some comments down below, greatly appreciate it. And we will see you guys next time. Have a great afternoon.